Hi everyone. In the previous classes, we have seen various kind of implementations of synchronous counters, right? So means we have implemented with help of T flip-flop, D flip-flop, JK flip-flop, or some kind of X flip-flop also in one of the example, right? Yes. So in the earlier classes, in addition to this, I have given one kind of indication. These synchronous counters are also used for purpose of shift counting. We can call it as shift counters. So in today's class, I will try to go with these shift counters. So shift counters means what? They are just shifting its values. Shifting its values. Like for example, if I try to say 0, 1, 0, 3 bits are there, assume, right? Yes. So it will shift its positions, right? If it is going to shift its positions, so 0 towards right side, this 1 towards right side, this 0 towards this side, then what might happen? 0, 0, 1. Next, once again, if I try to shift this towards right side, what will happen? 1, 0, 0. Next, if I try to shift, you are going to get 0, 1, 0. So this is a kind of a shift counting. So it is going to behave between, it is going to alter between these values only, right? Meaning that 0, 1, 0, 0, 0, 1 and 1, 0, 0. That's it. So this is one of the example for shift counters, right? Yes. So basically, if you look into the various types of shift counters, they are classified into two types of counters. One is a kind of ring counters. Another type is Johnson counters. Johnson counters, right? These Johnson counters, they are also calling it as fisted or switch tail ring counter, right? The reason why they are calling this, I will explain while explaining the Johnson counter. Okay, fine. So if I say it's a kind of a ring counter, there is a small difference between the ring counters and the Johnson counters. Okay, fine. So now let us try to discuss the first one, ring counter. So ring counter is a kind of shift counter. So I can say that shift ring counters. So ring counters means your values are going to be produced in the form of some kind of ring. I mean, it's not exactly the thing. If we go with some kind of mod 2 ring counter, we are going to have basically, guys, two flip-flops. So this is the difference between the earlier kind of counters and this counter. In the earlier kind of counters, if you are going to have two flip-flops, we are going to get 4 states. We are going to simply call it as a mod 4 counter also. Mod 4 asynchronous ripple counter, like that we are calling. But coming to the ring counter, the difference between the other counters on this ring counter is, if I say that mod 2 ring counter, it has to have compulsory required 2 flip-flops. That is the difference between the other flip-flops, other counters and this counter. Okay, fine. See, as I am saying that this is a kind of synchronous counters, you have to have simply pass the corresponding clock. And if you assume that this is a kind of D flip-flop, it is D0 and this is Q0, this is D1 and this will be the Q1, right? Yes. Now, when we can say that this is a ring counter means, if it acts as a kind of some ring, it acts as a kind of a ring, right? If you are able to observe, if it is connected to this one, what might be happen? The value of D1 is depend on Q1. That's okay, good, fine. Yes. Now the value of D0 have to depend on Q1. Then it's a kind of a ring. I mean, what we can say na, in ring counter, the last output connected to first input, then you can call it as a ring counter. Ring counter. So last output means, if I say in terminologies, if I say as qn minus 1, am I right or not? Right. So this is q0, q1 and so on, qn minus 1. Qn minus 1 is connected to I not input. I can be any kind of flip flop again. I can be any kind of flip flop. Whereas coming to Johnson counter, it is somewhat different. The first input is connected, which was produced by the last output only, but that last output is not actual output, it's a complement output, meaning that if you are able to clearly observe, this is q1 bar, right? If q1 bar is going to be connected to d0, then I can call it as Johnson counter. The reason why we are moving for that is, let me tell that, right, later point. So this is what the definition of thing, right? Yes. So simply, if I look into drawing the diagram, all are going to be connected like this, and this will be connected like this, right? This is what a ring counter. But coming to Johnson counter, the input of this one is going to be connected by the complement one. So this is q1 minus 1 bar. This will be connected, not this q1 minus 1. Okay, fine. And remaining thing are all as usual. That is the difference between ring counter as well as Johnson counter. Okay, fine. Now coming to the implementation part once again. Right, guys, here my requirement is, if I am going to have 1 0, if I am going to have 0 0, it will be, if I am going to apply a ring on this one, what will happen? It is going to be always 0 0 only. If I am going to have 1 1, if I am going to apply shifting of bits, it is going to be always 1 1. If I am going to have 0 1, if I shift, what will happen? It will get 1 0. If I am going to apply shift on this one, it is going to get 0 1. If I apply shift on this one, you are going to get 1 0, right? So this is the outcome what we are going to get in mod 2 ring counter. But how you will get that, right, guys? Basically, if you are going to have 0, assume that initial state is, see, for example, if I call the d1 and d0, or instead of taking the d1 and d0, first let me take the q1 and q0, because those are the present states we require, right? So 0 0, 0 1, 1 0, 1 1. These are the present states. Once these are the present states, you have to guess what might be the next states. What might be the next states means what? q1n and q0n, right? So you know, if it is 0 0, you need to have 0 0. If it is 1 1, you have to have 1 1. If it is 0 1, you have to have 1 0. If it is 1 0, you have to have 0 1. That you can able to get its next states also, right? These are the present states. Right? But the thing is, you should not write this directly, right? The point is, you have to go through the equation generation, so as like we did earlier. So if you want to have the q1 next value, so q1 next value is going to be determined by d1. D1 value is going to be determined by q0. So q1 n value is will be d1. D1 value is q0. So q1n I can write as indirectly as q0. So 0 1 0 1 0, right? Similarly, q0n you can write it as d0, but d0 is what? q1. So q0n as 0 0 1 right? Now if you are able to simply draw the diagram, from 0 0 you are going to get 0 0 only. 0 1 it is moving to 1 0. 0 1 it is moving to 1 0. From 1 0 it is moving to 0 1. From 1 1 it is moving to 1 1 itself. So simply you can able to understood this particular state diagram counting of either only single zeros or number 3 or a kind of 2, right? 2 counting, right? So I can call this as mod 2 counting. This as mod 2 counting. But in the situation, how it is actually working? See, if I say that these are something like 1 0 or 0 1, 1 0 or 0 1, how it is going to work? Just think about it. They are going to simply shift the values, right? So for example, if I say that the initial values are q0 value is 0, q1 value is 0, 0. If until clock is passing, always you are going to get iterated, right? 0 0 0 0. For example, if I say in place of this 0, it will be 1. If I give 1 0, what will happen? For the first clock signal, 1 0 are the inputs, that's okay. But if I apply the next clock signal, what will happen? This 1 will be produced at this point and this 0 will be get at this point, at this point this 0 will be get, right? Then if I apply the clock signal, you are going to get 0 1. So this is where 1 0 you are going to get as 0 1, as 0 1. But is there any chance to get these values 0 0 1 1? See, I am trying to explain. If you are in the state of 0 0, definitely you are going to get always 0 0. If you are in the state of 1 1, definitely you are going to get always 1 1. If you are going to the state of 0 1, you are going to get 1 0. If you are going to get in the state of 1 0, it is going to produce 0 1. That is okay. But in this single circuit diagram, can you able to get all these things? That is my question. Yes, we can get. When you can get this, I will try to let you know. So you can just think, right, guys, when we are explaining the concept of asynchronous inputs of JK flip-flop, either in active low or in active high, when you are going to produce always one, when pre-state is 0, and clear equal to let me call any value, clear equal to 1, then you are going to get the next state value as always 1. When pre-state is 1 and clear equal to 0, priority will be given to clear, so your next state will be always going to be 0. So at this point of time, your circuit can act as all these kind of things. So that's the reason what I can do now. I will try to make use of some pre-states. So if I try to connect this one for some kind of clock, this is a kind of clear signal. If I make it clear, right? Suppose for example, if you have passed this signal, as 0, what might be happen? So as I have connected this one, this is pre-state, right? So if I am going to pass 0 here, what it might think that this is clear is 1. When clear is 1, so this state value you are going to get as 1. Right? Yes. So if it is 0, this is 0, here it is going to produce a value as 0. Now if I am going to have the rotation, you are going to get always 1 0 0 1 toggling. But if I pass the clear value as 1, so let me take it with another color, clear value as 1. So now pre-state value as 1. When pre-state value as 1, then definitely is going to be in 0, and this will be in 1. So like this it is going to work. Okay? So this is the way you can able to work with the ring counters, guys. But you don't worry about this pre-state and clear always. So once you get this kind of thing, if you are able to solve this particular thing, that's enough for us. Okay, I hope I understood clearly. Thank you.